discovery beneath the Cascade Mountains as researchers uncover a massive water reservoir.
Well, the Oregon Cascades are a favorite place for skiers and snowboarders this time of year.
The first signs emerged when a series of high-resolution thermal satellite scans began registering anomalous heat signatures beneath the rugged spine of the Cascade Range. Scientists, initially skeptical, rechecked the readings over multiple orbits, expecting some quirk of reflection or seasonal melt to explain the data. Instead, the results became more consistent and more alarming. A broad subsurface corridor of elevated heat stretched between three of the Pacific Northwest's most iconic and volatile volcanoes, Mount Rainier, Mount St. Helens, and Mount Hood. The pattern was not a scatter of unrelated anomalies. It was a continuous, branching network, its thermal profile indicative of moving magma. Before we start, smash the like and subscribe buttons for more updates. By the time the United States Geological Survey released its official Red Alert Bulletin, the research teams already understood the gravity of the situation. Magma tunnels, long theorized but never confirmed between these particular peaks, appeared to be active conduits of molten rock. Such formations suggested that the volcanic systems were not isolated threats, but rather interconnected components of a single immense magmatic network. This revelation carried with it the unsettling implication that pressure changes or activity at one volcano could directly influence the stability of the others. The Cascade Range has always been a place where geology flexes its raw, unpredictable power. Glacial caps cling to summits that sit atop deep, restless chambers. Their histories, written in ash layers, pyroclastic fans, and lava flows that shape the valleys. Yet to think of Rainier, St. Helens, and Hood as linked beneath the crust challenges the conventional understanding of these mountains. Each has its own personality. Rainier with its massive ice fields and lahar potential, St. Helens with its recent history of explosive fury, and Hood with its towering presence over Oregon's skyline. Connecting them via subsurface magma tunnels reframes the narrative from individual hazards to a unified geological system. The Red Alert designation is not handed out lightly. It signals the highest level of concern for potential volcanic activity and is usually associated with imminent eruption risk. In this case, it was not a single peak showing signs of eruption, but a recognition that the entire regional volcanic framework might be under shared stress. The USGS statement referenced significant shifts in subterranean seismic patterns, harmonic tremor signatures stretching across multiple monitoring stations, and satellite interferometry showing subtle but broad deformation of the land surface. Such deformation, when aligned with thermal anomalies, often indicates movement of magma into new or expanded pathways. To detect these tunnels, scientists used a combination of satellite-mounted infrared spectrometers, radar-based ground deformation measurements, and gravitational anomaly mapping. The thermal imaging revealed the warmth of molten material far below the surface, but it was the radar interferometry that painted the clearest picture, a faint, undulating pattern of uplift that paralleled the thermal corridor. Gravitational mapping confirmed that beneath the snow, rock, and forests, there were density variations consistent with molten rock channels. The convergence of these independent methods left little doubt. The geologic mechanics behind such a connection are rooted in the region's tectonic setting. The Cascades sit atop the subduction zone where the Juan de Fuca plate dives beneath the North American plate. This process forces water-rich oceanic crust deep into the mantle, where the added fluids lower the melting point of the surrounding rock, producing magma. In a complex volcanic chain like this, deep magmatic bodies can sometimes form links when pressure and stress conditions align. These tunnels are not hollow caverns. They are pressurized pathways where molten rock pushes forward, melting and assimilating the surrounding crust as it moves. With Rainier at the northern end of this network, St. Helens in the center, and Hood to the south, the implications of a connected system are immense. A surge of magma beneath one volcano could relieve pressure locally, but send a pulse of molten rock toward another, potentially triggering new intrusions or even eruptions far from the initial source. In practical terms, this means the region's emergency planning cannot focus solely on one mountain at a time. Any sign of instability might have cascading effects. The history of the region lends weight to these concerns. St. Helens' 1980 eruption was a single mountain event, devastating but contained within its own magmatic plumbing. Now, with evidence of these tunnels, the scenario shifts from an isolated blast to a possible chain reaction. Scientists are not suggesting all three volcanoes would erupt simultaneously, but they acknowledge that the stress transfer and magma movement between them could create complex, unpredictable activity over weeks or months. Communities living within sight of these mountains have long lived with their presence as both natural beauty and latent threat. Ski resorts, hiking trails, farmlands, and urban centers exist in the shadow of peaks whose slopes tell the story of past destruction. The discovery of this subterranean network forces a new layer of understanding, that what lies beneath is not a series of separate fuses, but perhaps a single braided cord. From a monitoring perspective, the challenge now expands exponentially. Each volcano in the system already has its own network of seismographs, GPS stations, and gas sensors, all tuned to detect changes in volcanic behavior. With confirmation of these tunnels, scientists must integrate the data from all three into a unified model, looking for patterns that cross traditional boundaries. A tremor beneath Hood may be more than local noise. It could be the distant echo of a magmatic surge originating near St. Helens or Rainier. In the field, volcanologists have begun deploying additional portable monitoring equipment along the suspected tunnel pathways. Helicopters ferry sensitive instruments to ridgelines and remote clearings, where they can triangulate seismic waves and sniff for trace volcanic gases escaping from hidden fractures. The hope is to catch the earliest possible signs of magma migration. Subtle shifts that might precede more dramatic seismic swarms or surface deformation. The satellite data that sparked this alert is being continually updated, with fresh orbits scanning the corridor every few hours. These readings provide near real-time thermal snapshots, allowing analysts to see whether the magma's heat signature is intensifying or moving. In combination with ground-based data, this offers a rare opportunity to watch a magmatic system in dynamic motion. What remains most striking to scientists is the scale. Magma tunnels of this length, spanning tens of miles between major volcanic centers, are not common in continental volcanic arcs. They speak to an unusually large and robust magmatic supply, capable of sustaining multiple active volcanoes over geological timescales. This raises questions about the deeper source feeding the system. Some geophysicists suspect there may be a vast, partially molten zone in the mantle beneath the southern Washington and northern Oregon Cascades, a reservoir far larger than the individual chambers mapped beneath each peak. The red alert is as much about the potential for sudden change as it is about the current conditions. Volcanic systems can remain in a heightened state of activity for months or even years without producing a major eruption, but they can also transition from relative calm to explosive violence in a matter of days. The interconnected nature of this network means that predicting such transitions is more complex than ever before. Pressure equalization, magma chemistry mixing, and volatile gas buildup could happen in one section, while stress quietly accumulates in another. Meteorological conditions add another layer of complexity to the picture. Rainier and Hood both carry significant glacial ice, and an eruption, or even strong geothermal heating, could rapidly melt large volumes of it. Such meltwater could mix with volcanic debris to produce lahars, dense, fast-moving mud flows capable of wiping out valleys far downstream. The possibility that multiple peaks could destabilize glaciers in different locations at roughly the same time makes hazard modeling a far more daunting task. From a purely geological standpoint, the tunnels are a breathtaking discovery. They transform the perception of the Cascades from a line of isolated vents to an integrated volcanic superstructure. For researchers, the find opens new avenues of study into how magmatic systems evolve, interact, and potentially synchronize their activity. For the millions who live within range of these volcanoes, the knowledge is sobering. The mountains have always been alive. Now it is clear they are also in conversation with each other, deep below the surface. The USGS teams are working closely with state and local authorities to translate this new geological map into practical guidance. While the red alert signals a need for heightened vigilance, it also reflects a proactive stance to study, to monitor, and to prepare before the system forces its hand. The satellite detections are just the beginning of what will likely be a long period of intense scientific scrutiny, with each data point feeding into models that might one day forecast the behavior of this newly revealed magmatic network. This discovery reshapes the mental map of the Pacific Northwest's volcanic heart. It invites both awe and unease, blending the wonder of uncovering hidden structures in the earth with the sober understanding of what they could mean. The magma tunnels connecting Rainier, St. Helens, and Hood are not mere geological curiosities. They are dynamic arteries in a living system, pulsing with molten rock, shaping landscapes in ways both gradual and catastrophic. The red alert is a call to watch closely, to respect the power beneath, and to recognize that the story of these mountains is far from finished. Beneath the rugged peaks of the Cascades, the newly identified magma tunnels carry with them an unsettling implication about the forces shaping the region. These are not stagnant channels. They are dynamic pathways in which molten rock is in constant slow migration, driven by pressure differentials and the buoyant rise of material from deeper in the mantle. This movement is not random. It follows structural weaknesses in the crust, exploiting fractures, faults, and ancient intrusive bodies that offer the least resistance. Over centuries, these paths can widen, narrow, or branch, but the current findings indicate that they are active and capable of transmitting significant volumes of magma between major volcanic centers. The detection of these tunnels changes the framework by which geologists interpret volcanic signals in the Pacific Northwest. Traditionally, a spike in seismicity under Rainier would be read as a local phenomenon, relevant mainly to that peak. Now such an event might be seen as part of a broader pattern, possibly signaling magma redistribution through the interconnected system. This perspective requires not only technical adjustments in monitoring strategies, but also a philosophical shift in how risk is understood and communicated. Volcanic unrest, once considered site-specific, must now be evaluated in the context of a multi-volcano network. From a tectonic standpoint, the formation of such a network is a testament to the immense and sustained heat source beneath the region. The subduction of the Juan de Fuca plate has been ongoing for tens of millions of years, feeding a line of volcanoes from Northern California to British Columbia. But the precise geometry and depth of magmatic linkages have remained elusive, masked by the complex layering of the crust and the chaotic signals of seismic noise. The current discovery pierces through that uncertainty, revealing a direct physical connection that geophysicists have long suspected might exist but could not prove. The implications stretch far beyond the immediate hazard. Such a system, if it remains active over geological time, could influence the chemical evolution of the magma feeding each volcano. Magma traveling through tunnels between chambers may mix with material from different sources, altering its composition, viscosity, and volatile content. These changes can affect eruption style, potentially turning what might have been a slow, effusive event into something more explosive, or vice versa. The blending of magmas also introduces unpredictability, as different chemical interactions can occur suddenly, creating conditions for rapid gas exsolution and violent eruptions. The current monitoring response reflects the urgency of understanding this subterranean circulation. Drone-based thermal surveys are being flown over remote flanks of the mountains, scanning for subtle fumarolic activity that might betray the presence of shallow intrusions along the tunnel paths. Gas samples taken from vents and springs are being analyzed for shifts in carbon dioxide and sulfur dioxide ratios, which can indicate fresh magma degassing from depth. These readings are critical because they provide real-time clues about the movement of molten rock, complementing the broader satellite-based observations. In the realm of geophysical modeling, supercomputers are being tasked with simulating the conditions under which such tunnels could form and persist. These simulations incorporate seismic tomography data, crustal stress maps, and heat flow measurements, creating three-dimensional reconstructions of the region's magmatic plumbing. The early results suggest that the tunnels lie at depths of roughly 10 to 20 kilometers, deep enough to be buffered from surface cooling, but shallow enough to interact with mid-crustal magma reservoirs. Such positioning makes them both effective conduits and potentially vulnerable to changes in pressure caused by eruptive events. The interconnected nature of these tunnels raises the question of whether historical eruptions in the Cascades may have been influenced by unseen activity in neighboring volcanoes. Records from indigenous oral histories and early settler accounts speak of periods when multiple peaks appeared restless within a short span of years. While these were often dismissed as coincidental, the new evidence suggests a possible underlying mechanism, a pressure disturbance in one part of the network, propagating along the tunnels to awaken another segment of the system. In terms of hazard management, this means that forecasting must now be regional in scope. It is no longer sufficient to issue warnings based solely on localized measurements. Authorities will need integrated models that can account for magma displacement between volcanoes. This will likely involve a more sophisticated public communication strategy, ensuring that communities understand the interconnected risk without causing undue panic. The goal will be to convey that an uptick in activity at one volcano is not necessarily a guarantee of immediate danger at another, but it does alter the overall probability landscape. Field teams are also studying the role of hydrothermal systems in this new dynamic. Both Rainier and Hood are known to host extensive networks of hot springs and fumaroles, evidence of circulating fluids heated by magma at depth. These systems act as pressure valves of sorts, allowing gases to escape and heat to dissipate. However, if magma begins moving more aggressively through the tunnels, these hydrothermal features could become supercharged, potentially destabilizing slopes or triggering small phreatic explosions. Such events, while not as catastrophic as full-scale eruptions, can still be dangerous to anyone nearby. One of the most intriguing scientific angles is the possibility of magma pulses moving through the tunnels in waves. Just as a heartbeat sends a surge of blood through arteries, changes in pressure at one volcanic reservoir could send a surge of molten rock racing toward another. This could manifest as a sudden increase in seismic tremor at the receiving volcano, followed by changes in gas output and ground deformation. Detecting and tracking such pulses could become a critical part of future volcanic forecasting, offering precious lead time before more significant events. Researchers are also considering the long-term geological implications. Over tens of thousands of years, such tunnels can act as assembly lines for large volcanic edifices, channeling magma to build up successive eruptions in one location before shifting to another. This could explain certain patterns in volcanic growth observed in the Cascades, where periods of intense activity seem to migrate north or south along the range. If the current tunnel system remains active, it may shape the future landscape of the Pacific Northwest in ways that will only become evident to distant generations. The scale of the discovery has prompted an unprecedented collaboration between American and international volcanic research institutions. Teams from Japan, Iceland, and Italy, countries with extensive experience in monitoring complex volcanic systems, are sharing expertise and instrumentation. In particular, Italian researchers from the Campi Flegrei region, where interconnected magma systems have been studied for decades, are contributing models that might be adapted to the Cascades' unique tectonic environment. Such partnerships are vital, as the complexity of the system defies simple extrapolation from single volcano behavior. From a cultural perspective, the finding resonates deeply with indigenous communities who have long held oral traditions describing the mountains as living, communicating beings. Stories passed down over centuries speak of these peaks as members of the same family, sometimes quarreling, sometimes speaking to one another through the earth. While science and mythology operate in different realms, the new evidence of physical connections beneath the mountains gives these traditions a new layer of resonance, highlighting how human understanding of the land can be both symbolic and empirical. Economically, the stakes are significant. The Cascade volcanoes are not just natural wonders. They are focal points for tourism, recreation, and regional identity. The knowledge that they are connected by active magma tunnels could alter investment patterns, infrastructure planning, and even insurance models. Communities that once considered themselves outside the primary hazard zones for a given volcano, schools in the region have long taught students about their local volcano, but now curricula will likely shift to emphasize the interconnected nature of the entire Cascade Arc. This broader view can help future generations understand that volcanic risk is not confined to a single mountain, and that preparedness is a shared responsibility across state and county lines. The technical demands of monitoring such a system are formidable. Continuous satellite coverage must be maintained despite competing global priorities, requiring coordination between NASA, NOAA, and international partners. Ground-based sensors must be robust enough to survive harsh alpine conditions, with redundancy built in to prevent data gaps during severe weather. The data pipeline itself must handle vast amounts of information, integrating seismic, thermal, gas, and deformation readings into coherent, actionable reports in near real time. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on magma tunnels? What do you expect will happen next? We want to hear from you. Thank you for watching and see you next time.